3,000 years ago, Persian engineers cooled entire cities to comfortable temperatures in the middle of a desert where summer highs exceeded 104 degrees Fahrenheit. No compressor, no refrigerant, no electricity. They buried clay pipes underground and let the earth do the work. The modern air conditioning industry made sure you never learned about it. By the end of this video, you will discover why and how to build one yourself. I'm Eddie, and welcome back to Construction Odyssey. Subscribe so you never miss what the cooling industry hopes stays forgotten. Every ancient civilization that endured extreme heat independently arrived at the same conclusion. The earth stays cool. Push air through enough underground mass and the ground becomes the air conditioner. The Persians proved it with the Qanat and the Badjir. The Egyptians proved it with subterranean ventilation shafts. The Romans proved it with the cryptoporticus. Different continents, different centuries, identical physics. In ancient Persia, as early as the 7th century BCE, engineers constructed qanats. These were underground water channels carved through bedrock, stretching for miles beneath the desert. Hot, dry air entered vertical shafts and traveled along channels lined with cold underground water. By the time that air reached the building above, it was cool enough to make desert summers survivable. Paired with towering wind catchers called badgers, these systems created continuous airflow through stone homes without a single moving part. In the city of Yazd in central Iran, a towering 33-meter wind catcher still stands in the Dawlatabad garden. It uses neither electricity nor polluting materials. It simply catches the wind and drives it underground, where the earth strips away the heat. UNESCO recognized the Persian Qanat as a World Heritage Site in 2016, not because it was a relic, because it still works after 3,000 years. The Romans applied the same technique at massive scale, building the 5,653-meter tunnels of Claudius, with shafts sinking over 122 meters deep. In Palermo, Sicily, a Qanat network built during the Arab period cooled the entire city. The famous Scirocco room in Palermo still uses water flowing through a qanat combined with a wind tower to cool interior air today. Different empires, different tools, the same discovery. The ground below a certain depth holds a nearly constant temperature regardless of what happens on the surface. The modern version of this ancient system is called the earth tube. Some engineers call it the Canadian well. The physics have not changed since Persia. At roughly 2 meters below the surface, the soil maintains a nearly constant temperature of 10 to 13 degrees Celsius throughout the entire year. Summer heat waves do not reach it. Winter freezes do not touch it. The earth at that depth is a thermal battery that never runs out. You bury a long pipe underground. You draw outdoor air through that pipe using a small fan. On a brutal summer day, outdoor air enters at 35 degrees Celsius. As it travels through 100 to 200 feet of buried tube, the surrounding cool soil absorbs the excess heat. By the time that air exits into your home, it has dropped by 20 to 30 degrees Fahrenheit. No compressor, no chemical refrigerant. One small fan consuming roughly 50 to 100 watts. In winter, the process reverses automatically. Freezing outdoor air enters the tube, and the stable ground temperature warms it. Free heating and cooling from a single buried tube year-round. The Earth Rangers Center near Toronto, Canada uses 9 concrete earth tubes, each 20 meters long, buried 3 meters underground. In winter, the system warms incoming air by as much as 20 degrees Celsius. In summer, it cools air by 10 degrees Celsius. A 2025 study published in Scientific Reports documented yearly energy savings reaching 74% in Milan and over 60% in Palermo when earth-air heat exchangers were integrated with air handling units. The Cambridge Public Library in the United States uses 42 buried earth tubes, achieving 51 to 56% lower total energy use compared to a standard building. And the system lasts 50 to 100 years. Compare that to mechanical HVAC units that last 15 to 25 years before ending up in a landfill. So why is there not an earth tube under every new home? The answer has everything to do with money and nothing to do with science. The global HVAC system market was valued at $174.58 billion in 2025. Executives in corporate boardrooms depend on that number growing. American consumers spend over $10 billion annually on HVAC repair and maintenance. Technicians in branded vans pull into driveways every summer. The average customer lifetime value for a single residential HVAC client is $15,340. Now picture an earth tube. One installation, one trench, one pipe. No compressor to replace every 15 years, no refrigerant to recharge, no filter subscriptions, no annual service contracts. One fan that costs pennies per day to operate. A lifespan measured in half centuries. One sale and then silence. Zero recurring revenue for anyone. The HVAC business model depends on equipment that degrades, bills that recur, and replacements that repeat. An earth tube breaks every single link in that chain. No corporation in a $174.58 billion industry had any reason to tell you about it. The regulatory system finished the job. Earth tubes are not explicitly banned, but they face something worse. They are completely unaddressed. The International Residential Code contains no provisions for earth-air heat exchangers, no testing protocol, and no installation standard. When a building inspector encounters something the code does not cover, the default answer is always no. Not because the system is dangerous, but because nobody wrote the rule that says it is allowed. The primary objection inspectors raise is radon. Indoor radon exposure causes approximately 21,000 lung cancer deaths in the United States each year. That concern is legitimate, but Europe took a different path. When early installations in Austria, Denmark, and Germany revealed problems with condensation and mold from sloppy installation, the Europeans developed proper standards and taught people how to build them correctly. Earth-air heat exchangers have been common in European residential ventilation since the mid-1990s. The American response was to pretend the technology does not exist. But you do not need anyone's permission to understand the physics. Here is exactly how to build one yourself. Before you pick up a shovel, you need 3 pieces of information: your soil type, your water table depth, your local radon zone. Pull up the EPA radon zone map and find your county. Zone 1 means elevated radon risk and demands fully sealed pipe joints and mandatory post-installation testing. Know your soil. Clay and moist soils conduct heat far more efficiently than dry sandy ground. And know your climate limitations. Earth tubes are less effective in hot, humid regions like Florida, where dehumidification becomes the real engineering challenge. Use smooth wall, high-density polyethylene or PVC pipe. Minimum 6-inch diameter. 8-inch for larger homes or warmer climates. The inner surface must be completely smooth. Corrugated pipes trap condensation and breed mold. For maximum protection, use antimicrobial lined pipe. Companies like Amvic manufacture complete residential earth tube kits with 180 feet of 8-inch pipe infused with silver nitrate plus prefabricated stainless steel inlet towers, filters, and condensate sumps. Your total pipe run should measure 100 to 200 feet. Maintain a minimum 6 feet of spacing between parallel runs. Slope the entire system at a minimum 2% grade toward a condensate collection point. That consistent downhill slope prevents moisture from pooling inside the pipe. Trench depth is non-negotiable. Minimum 6 feet. At that depth, ground temperature holds steady at roughly 6 to 8 degrees Celsius year-round. Bed the trench bottom with 4 inches of compacted sand or pea gravel. Lay the pipe on that prepared bed. Backfill with granular material for the first 12 inches above the pipe, ensuring complete contact. No AIR gaps anywhere. Air gaps destroy thermal transfer. Seal every joint in the buried section. Solvent weld for PVC. Fusion weld for HDPE. These welds are simultaneously your radon barrier and your groundwater barrier. The air intake rises vertically at the far end, terminating at least 12 inches above ground level with a screened downward-facing cap. Position it away from driveways and exhaust sources. Inside the house, connect the earth tube to a heat recovery ventilator or an energy recovery ventilator. One documented Canadian installation found this combination boosted the heat pump coefficient of performance from above 3 to as high as 5. The earth tube made every other mechanical system in the house work better. Install an inline fan rated for 100 to 300 cubic feet per minute. Add a condensate trap at the house entry point and mount a MERV 13 filter on the discharge side. And install a continuous radon monitor in the mechanical room. That step is non-negotiable regardless of which radon zone you live in. For homeowners in high radon areas, there is a powerful second path, the closed-loop glycol earth tube. Instead of running air through buried pipes, you circulate a water and glycol mixture through a buried loop. That tempered fluid passes through an air to liquid heat exchanger inside the house. No radon pathway, no condensate in the pipe, no mold risk. It delivers 80 to 90% of the thermal benefit while remaining code compliant under existing plumbing provisions in every state. Heating, ventilation, and air conditioning systems account for up to half of a building's total energy consumption. Earth tubes attack that number at its root. Not with more sophisticated equipment, with less complexity, less machinery, less dependence on a grid that fails exactly when you need it most. When the grid goes down during a heat wave and conventional air conditioning dies, the earth tube keeps working. The ground does not need electricity, it does not send a bill, it does not break down after 15 years. The Persians solved cooling 3,000 years ago with a trench, a pipe, and the patience to let the earth do what it has always done. The temperature at 6 feet is the same today as it was when Sargon II marched through Persia. The physics still work. The pipe is waiting. Now you know not just why this was hidden from you, but exactly how to build it yourself. Subscribe to Construction Odyssey with Eddie. Please watch the next video appearing on your screen right now.